Digital logic. Minimization techniques. This presentation will explore essential techniques for minimizing Boolean expressions, a critical skill in digital circuit design. We'll cover both foundational algebraic methods and the powerful graphical approach of Karnaugh maps. Agenda. Why minimization matters. Efficiency. Cost reduction. Reduce the number of logic gates and inputs required in a circuit. Fewer components mean lower manufacturing costs and smaller board space. Performance. Reliability. Simpler circuits exhibit faster propagation delays and consume less power. Reduced complexity generally leads to fewer points of failure. Chapter 3. Foundational concepts. Boolean algebra. Sum of products, SOP. SOP is a method of expressing Boolean functions as a sum, OR, of product, and terms. Each product term represents a specific combination of input variables that results in a 1 output. Each product term is called a minterm. Variables in a minterm appear in either true or complemented form, e.g., A, B, C. Minimization in SOP aims to combine minterms to eliminate redundant literals. Comparing algebraic forms, SOP versus POS. When to use which? SOP and OR logic, POS, OR and logic, more intuitive for functions with many 1 outputs. More intuitive for functions with many 0 outputs. Directly implements logic using AND gates followed by an OR gate. Directly implements logic using OR gates followed by an AND gate. Example. Safety system requiring specific conditions to be met for an alarm, e.g., temperature and pressure and smoke. Example. Control system disabling operation if any of several fault conditions exist, e.g., overheat OR low oil, AND, power loss OR malfunction. Graphical minimization. Introducing the Karnaugh map, K-map. The Karnaugh map is a graphical method for simplifying Boolean expressions, especially effective for up to 4 variables. It leverages the human ability to recognize patterns. Visual representation. Adjacency. Grouping. Groups of 2n adjacent, 1s, or 0s, are identified to eliminate redundant variables. A grid where each cell corresponds to a minterm, or maxterm, of the Boolean function. Adjacent cells, including wraparound, differ by only one variable, allowing for direct combination. Grouping. Groups of 2n adjacent, 1s, or 0s, are identified to eliminate redundant variables. K-map construction. 3 and 4 variables. As the number of variables increases, the K-map size grows exponentially. 3-variable K-map, 4-variable K-map, has 2 to the power of 3 equals 8 cells. Has 2 to the power of 4 equals 16 cells. Typically arranged as 2 rows and 4 columns, or vice versa. Arranged as 4 rows and 4 columns. Column, row labels must follow gray code, e.g., 00, 01, 11, 10. Both row and column labels follow gray code sequence. K-map construction. 3 and 4 variables. As the number of variables increases, the K-map size grows exponentially. 3-variable K-map, 4-variable K-map, has 2 to the power of 3 equals 8 cells. Has 2 to the power of 4 equals 16 cells. Typically arranged as 2 rows and 4 columns, or vice versa. Arranged as 4 rows and 4 columns. Column, row labels must follow gray code, e.g., 00, 01, 11, 10. Both row and column labels follow gray code sequence. K-map grouping rules. Simplifying with K-maps. Form groups of powers of 2. Largest possible groups. Group 1, 2, 4, 8, or 16 adjacent 1s. Always form the largest possible groups, even if it means overlapping. Overlap allowed. All 1s must be covered. Cells can be part of multiple groups. Every 1 in the K-map must belong to at least one group. Key takeaways and next steps. Minimization is key, crucial for efficient, cost-effective, and reliable digital circuit design. SOP, POS for basics. Understand both algebraic forms for representing and simplifying Boolean functions. K-maps for practicality. Master K-maps for up to 4 variables. They are the industry standard for manual minimization. Practice is essential. Work through numerous examples to develop proficiency in grouping and deriving minimized expressions.